Welcome to my lab on oscillations. So the purpose of this lab is to observe the motion of spring oscillating in x and y directions, and then to compare this motion in a real-life scenario to a computational simulation. In this simulation, we'll also plot the changes in position, motion, and energy, and we'll specifically determine how kinetic, gravitational potential, and spring potential energies change during an object's motion, specifically a spring's motion. So the physics behind this, we'll first be working with Newton's second law and net force. The net force of this system should be the force of the spring plus force of gravity. At certain points, the net force will also be equal to zero when the force of the spring is equal to the force of gravity, and one of they're opposites of each other. At these points, the system will be in equilibrium. We'll also be using spring and gravitational potential energies, which their formulas are listed to the right, and we'll be using kinetic energy as well. Energy principle will also be important to what we're doing, as it is equal to the work of the surroundings plus the thermal energy that escapes the system. Both of those should be equal to zero, as there are no surroundings. So the change in energy should also be equal to the changes in potential energy plus the change in kinetic energy. And because, again, the change in total energy should be equal to zero, as there are no surroundings, all of that should be equal to zero. We'll also be using the velocity and position update formulas to get velocities and positions at different periods of time. So the reasoning behind these laws and models in second law net force is because the object has a bunch of forces acting on it. The spring and gravitational potential energies are because we have an object that has both spring and gravitational potential energies, which we are trying to find and see the relation with other aspects of the project. We're also trying to get the kinetic energy to see the velocity of the object in certain periods of time and the total energy that it has in motion. We are using the energy principle to find all these different kinds of energies, as it helps us set everything equal to zero and find different variables. The velocity and position update formulas are used to find velocities and positions, and free body force diagrams, which are listed to the right, are used to show the changes in forces over time. We can see that the forces are equal in equilibrium. The force of the spring is greater when it's below, and the force of the spring is smaller when it's above that equilibrium position. The force of gravity stays the same all the time, while force of spring changes. We'll also be using tracker and glow script to model our project. So a preview of results: the change in total energy should be equal to zero, and the model and the last scenario are very similar, and every different form of energy should oscillate. So the experiment used came from pre-lecture videos, and the mass is the object connected to the spring, or the position is where that mass is with respect to the attachment point, and the system is the Earth and the spring with mass, while the surroundings are nothing. When the spring is released, gravitational spring forces create velocity, and the initial velocity, however, will be 0 meters per second, and the initial position in the x direction will be negative 0.132 meters, while in the y direction it will be negative 0.626 meters. So here's tracker. I changed the start time to be this frame over here where the object is actually released, so you can see that the object is being tracked. Over here, you can see the positions in the x and y directions and graphs. At the bottom here, you can see a spreadsheet of all the different positions at different times. So here are the values and calculations for the computational simulation. To the left, you can see the computations we need to make to get the spring constant. If you look in the middle, you can see the mass of the ball, which was gotten from the pre-lecture videos, and you can also see the position of the ball, which we found in tracker. And if you look below that, you can see the gravitational constant. You can see the spring constant and the relaxed length of the spring, which we got from tracker and from the pre-lecture videos. Below that, you can also see calculations for the position of the ball, plus the L hat, and then the distance from equilibrium of the spring at any given point in time. And below that, you can also see calculations for energy. And to the right, you can see continuations of everything, where you see calculations for the forces. You can see calculations for energies, and that's all to update forces and energies throughout the object's motion. Here you can see the code for the simulation. If we run the program, you can see, and then if we put the CSV file in, you can see that the spring does its thing, and it models the real-life experiment. It also creates graphs below. So here are the graphs that came as a result of the computations that we put through GlowScript. You can see that the changes in energies all oscillated, except for the change in total energy, which remains zero. For y position versus time and x position versus time, you can see that they oscillated around the same rate. Simulators and differences, we saw that the experiment and model shared the same period and similar graph shapes, and they also had fairly similar amplitudes. However, the experiment amplitude was slightly smaller than the model, and the experimental x position had a slightly smaller period as well, which increased deviation results. And experiment data was also more jagged. We believe that a lot of the differences, however, could be explained through possible sources of error, which include things like the model failing to account for air resistance, or the initial velocity potentially being non-zero, or even just human error in the tracking, or fewer observed entries, or even just a camera angle error. So is the energy principle satisfied? Well, change in spring and gravitational potential energies are opposite, and the kinetic energy oscillates with them. All three of these energies always add together at any point to equal zero, and so the total change in energy in the system will always be zero. As a result, that means that the energy principle is satisfied, as the total energy is equal to zero, as no external forces are acting upon the system. So the estimation of oscillation periods, we estimated that the average oscillation period in the x direction would be around 1.63 seconds, while in the y direction it would be 1.52 seconds, and the oscillation period in the y direction, therefore, is somewhat shorter. We believe that differences in oscillation period could be due to external forces like drag, and that may also explain deviations between computation and experimentation. As we saw, there were slight deviations in the data from both, and that might help explain it. Some conclusions from our experiment and model. We saw that the change in total energy should equal zero. The model and real-life scenario are also very similar, and every different form of energy oscillates. Energy principle was shown within our results, as the energy was the change in total energy always remained zero, as no external forces were acting on the system, adding or taking away energy from it. And the energy and the energy principle are also shown to help model motion. Thank you for watching.